I'm going to be talking briefly, very briefly this morning, about some estimates we generated which characterize the change in population exposure and risk that we expect to see between 2005 and 2017. I should note that this work was done in collaboration with David Risley from the Office of Atmospheric Programs and my colleague Ken Davidson in the Office of Transportation and Air Quality. So there are three key questions I was hoping to answer with a data set that was available as part of the rulemaking process for the mercury and air toxic standards. And those are as follows. First, we wanted to know what the population-weighted change in total PM2.5 mass and PM species was going to be between 2005 and 2017, 2017 being relevant because it's the implementation year for mass. We wanted to know what highly populated parts of the U.S. will see the greatest and least reduction in sulfate during this time frame. Sulfate being relevant because it's the precursor, obviously, that's being affected the greatest by the MATS rule. And then also what mortality risks attributable to PM would change over time and over space, and how would those change by species? Okay, so first this question of population exposure. I think this graphic is particularly interesting because it shows a pretty substantial decline in total PM, total population weighted levels of PM that we expect to see between 2005 and 2017. The bars that are below the blue bar basically segment the change in pop-weighted PM by species. The purplish bar, sorry, the color's a little off because I think that projector is about to die, represent direct PM, sulfate, and nitrate. And what you see, maybe not surprisingly, is that sulfate between 2005 and 2017 represents a smaller and smaller proportion of total PM mass. So not only is total PM declining, but sulfate is declining at actually a higher rate than the other species. And I think this is something that's particularly important to bear in mind as we're considering how to design outcome research. This map, and I apologize, it's not quite as clear as I was hoping, illustrates the population-weighted, the overall change in sulfate expected between 2005 and 2017. The darker, or I should say the richer, redder colors indicate larger changes. The cooler colors represent smaller changes. The yellow outlines are identifying counties, or actually I think these are 12-kilometer grid cells, where we see the largest change in population-weighted sulfate. In other words, these are the locations where we see the largest change in sulfate among the most populated locations. The orangish color represents still large changes in sulfate, but smaller changes in sulfate, but still among highly populated areas. And then this is probably almost completely indiscernible by people in the back of the room, but these are the locations of PM monitors across the U.S. And the reason I superimposed these PM monitors was just to illustrate that we have fairly good geographic coverage among these locations where we're seeing sulfate changes in highly populated areas and smaller scale sulfate changes in highly populated areas. It's this type of information that could potentially be useful for outcomes research if we're looking at seeing large and small sulfate changes, but where we still want to have enough power to detect health impacts or health outcomes among the population. Okay, so very briefly, I just want to illustrate the changes in PM-related mortality risk that we expect to see between 2005 and 2017. First, starting with just looking at mortality risk due to changes in total PM mass. And what you see, maybe not surprisingly, is particularly in the eastern U.S., that the percent of deaths attributable to PM by county is falling pretty precipitously. So in the map on the left-hand side, which is the 2005, what we're seeing is a lot of areas in the eastern U.S. that are red, and those red areas basically disappear by 2017. What that's telling us is that the overall mortality risk attributable to PM is declining, in large part because of the MATS rule as well as a number of other federal rules and state rules. What's also interesting is if we look at the PM-related mortality risk, we break it into individual species. And let me note here that I'm still continuing to estimate mortality risk using risk coefficients that are not differentiated by estimating PM mortality risk using a hazard ratio drawn from the Krusky et al. Study. So it's not as though I'm trying to estimate differential toxicity here. I'm just taking the direct PM component and then estimating mortality risk. And what's interesting here is you see a slightly different geographic distribution of impacts. And what this suggests is that there is a differential effect on direct PM levels across the U.S., and that's in turn differential impact on risk. This map is looking at PM-related mortality attributable to sulfate changes, and maybe not surprisingly, you're seeing the largest drop in risk in the eastern part of the U.S. And then finally, just to round it out, this is PM-related mortality risk attributable to nitrate. And again, you see a different signal. And so those are all the maps that I have. And just in the interest of time, I suppose now